Hello, so do you see my screen?
I do, yes, thank you.
Is it full screen now?
Yep, yes,
Yep. So, hello, I'm Alain Quartier-la-Tente, a French statistician, and I'm going to talk about one of the R package around seasonal adjustment we are working on. It is called rjdfilters, and it allows to manipulate moving average and implements several techniques for real-time trend cycle extraction. So first, some reminders. I think you all know the seasonal adjustment method X13, well, which is based on the recursive application of different moving average. So as a moving average is just a random computation of a weighted mean of P base value and F future values. And the study of the property of a moving average is often done with two functions, the gain and the phase shift. Well, the idea is that when you apply a moving average to a periodic time series, it will have two effects. It will the level will be multiplied by a quantity called the gain, and the a phase shift will be created that implies that turning points will be detected with delay. Most of the symmetric moving average can be computed with a local polynomial theory. Well, in this theory, you assume that your trend can be locally estimated by a polynomial of degree d. And to estimate your trend at the date t, you use h observation before and after t. And the estimation is done with weighted least squares, and the idea of the weights is that to estimate the trend at the date t, you want to assign higher weights to the data that is close to t than to the data that is far from t. And while we can show that it's equivalent to apply a symmetric moving average, and with some specific parameter, you can find all the classical moving average as the arithmetic mean or the Anderson filter. So now let's talk about what already exists in R. Well, in the base package, you can already apply some moving average, but only some simple forms. So with this function, these parameters, you can use some symmetric moving average. So when you use as many future points than base point, you can also use some specific kind of asymmetric filters when you don't know any future points. Well, you could also add some zero in the weights on the first function to create a general asymmetric moving average, but well, it won't give satisfying results because you won't be able to directly compute the last points. And you also have some several packages that can be used for local polynomial models. They are more general, but you have you don't have lots of parameters, so you cannot create all these seasonal adjustment filters. And you also already have several packages to perform seasonal adjustment, but it can be tricky to isolate the effect of one specific moving average. So to sum up, there is no package that allows to easily manipulate moving average and specifically asymmetric moving average, and to analyze their properties like the gain or phase shift function. And while you cannot easily create the seasonal adjustment specific moving average like the Anderson or the Musgrave filter. And lucky for you, you now have a wonderful package that allows to do a lot of things that I will present today. It is based on the Java libraries of the seasonal adjustment software JDemetra Plus. And with this package, you can easily manipulate moving average and study their properties. You you can also use some different modern techniques to create asymmetric moving average that can be used for real-time trend cycle extraction. So to estimate the last point of your trend cycle. And you can also do some experiment changing the moving average used for the decomposition in the algorithm. So the package is in GitHub, and here you have a simple code with one way to install it. So let's first talk about moving average. So you have a function called moving average that allows you to create narrow objects from which you can do a lot of manipulation. Here I've created two moving average. One is a forward moving average, so you only use future points, and one is a center symmetric moving average. And then you can simply add them, subtract them, or multiply them to create a new moving average. Well, I find it useful because with those functions, you can, well, for example, very easily create all the moving average that are in the decomposition method X11. And here you have the code to create the central symmetric filter of X11. So I don't know if you have in mind the algorithm, but the idea is the following. First, we apply this specific moving average to have a first estimate of the trend cycle, and then we use it to have to estimate the seasonal plus irregular component, and then we apply this moving average on each month to get the seasonal component. So this moving average is applied to every January, every February, etc. So you have also function toSeasonal that allows you to, well, to convert this moving average that is applied to each period to one general moving average that will be applied to your raw data. For example, if the current date, so the date T, is a January, you see that you have you only use the over January month in the moving average, so like here. And then it's the same recursive idea while using in one step the Anderson filter. So finally, well, you have some function to plot the coefficient, to plot the gain and the phase shift function, and here I'll plot them for the final filters used to extract the trend cycle component and the seasonal adjustment component. And with a few lines of code, you can have well, those kind of results. And to apply them to data, it's really simple. Well, you just take your time series here, and you just multiply it to the R moving average object, and you have the result. So let's now talk a bit on asymmetric filters. So, well, the idea using X13 is not this one, but it can be simplified to this idea. Well, first, you take your time series that you extend it with a Naruma model, and so your seasonally adjusted series, and then you apply a symmetric Anderson filters on your extended data with some specific parameters and with some details. Well, while this is equivalent to use asymmetric filters, because you will the forecasts are linear combination of past values. And well, in some case, so you might want to use some different techniques, some specific asymmetric filters, especially around turning points. So several authors studied the alternative methods, and a few of them are implemented in the package. Well, the first one is based on local polynomial. So here you have the same slide as before, and the question is, well, what do we do for real-time estimates? So what do we do when you do not have here h future points? Well, the first simple idea would be to do the exact same thing, but with less future points. And this is, I think, for example, what is done in the STL seasonal adjustment method, and this is called the direct asymmetric filters. It leads to estimates that have, in theory, no bias, but we will see that have a lot of variance. So the idea of different authors is to introduce some bias on the estimate to minimize the variance. So here we find the so-called Musgrave filter, which assumes that for the last point, the trend is linear, and we constrain the asymmetric filters, so used for the estimation of the last point, to only reproduce with no bias constant trends. And same idea with quadratic linear and cubic quadratic filters. Those are linked to the INSEE ratio that can also be computed in the package. And well, I don't enter into detail, but you can also extend those methods to add the criteria that will control the time delay in detecting turning points. And this extension is also implemented in the package. So you can, for example, directly to extract the different moving average, use the alpha filter function, specifying the different methods, and plot the coefficient with the plot coef function. And well, simply analyzing the results, you can here directly see that with those filters, you will have a lot of revision between the first estimate, so that is computed with this moving average, and the last estimate, so computed with the Anderson filters. So there is also a second method based on the reproducing kernel Hilbert space theory. So I don't go into details, but the idea is that you can build a function called kernel function that will allow you to directly derive the coefficient associated to your symmetric filters after some normalization. And for the asymmetric filters, you can do the exact same thing, but you use less future points on the normalization. And here you have an important parameter, is the parameter B, and using a specific value and specific function, well, you can find all the symmetric filters that you can find with the local polynomial approach. So for example, you can find the Anderson filter, but some other idea used for the asymmetric moving average is to show this parameter with some optimization. So for example, minimizing some criteria. So here in this case is the phase shift. And well, the main drawback of this method is that in the optimization problems, you can have several minimum. So you might have different solution between the different software. For example, with the default values in the package, the solution found is this one, and whereas in the original paper where they presented this method, they found this solution. Well, I won't go into details in the last this method, but well, the idea is to do weighted mean of different criteria that measure some properties of the moving average. And well, one of the advantages is contrary to the previous method here in the minimization problem, you have a unique solution. So now let's go back to R and how to apply well this filter. So how to apply a set of asymmetric moving average and the final symmetric filter. So you have a function called JFilter that allows you to do that. It takes as an input all your asymmetric filters that are used in the estimation. So here you have the real-time asymmetric filter, so used to estimate your last point. And here you have your symmetric moving average, so used for the last estimate. So here is the Anderson filter, and well, just an example of on how to compute your INSEE ratio. And well, you also have a X11 function that allows you to change the filters used in the decomposition method. And what's interesting is that while here it's not mandatory to use a symmetric filter for the final estimate, the trend cycle component. So I just put here an example of a non-symmetric moving average for the last estimate, but it has no sense, but it's just for to have a simple example. And while you can plot the different results with the different moving average. So we will just see one quick example on comparing the different methods. Here, while you have different estimates of the US retail sales around the turning points of April 2020. So here you have the successive estimates of the trend cycle. For example, this one is the estimates that you have with the data known until April. Here the data known until May, and here into June, etc. And what you can quickly see is that with those polynomial filters, in that case, you have a lot of variance. And the Musgrave filters, in that case, can produce satisfying results that with less variance that when you extend your data with a Naruma model and then apply the symmetric Anderson filters. And well, one indicator and that can be interesting to check the quality of your last trend estimate is the implicit forecast. The idea is to do the reverse process use when you extend your data with a Naruma model. So you look at the necessary forecast of your input time series, which by applying the symmetric Anderson filters produce the same final estimate that we have with the different methods. So while with that indicator, you can compare your forecast to the forecast of the ARIMA model. And here you can directly see with the implicit forecast that we cannot trust the trend estimates with those methods. And you can compare the different forecasts with the forecast of the ARIMA model that are quite naive. And to sum up, I hope I have convinced you that with the RGD filters package, you can do a lot of useful things that you were not able to easily do it before. Well, I think it can be very useful for trainings when you want to explain the X11 algorithm, and because you can easily decompose the different steps. And for the futures, I already have some ideas on how to extend the package, but if you have any more idea, yeah, they are welcome. Thank you for your attention.
Oh, thank you, Alain. So you are the author of this package then?
Yes, I'm one of the author.
Great. Wow, that looks really extensive. Okay, we are